Good morning, everyone. My name is Amy David, and for this term, we work with industrial automation. And for my design project, I decided on an industrial chilling system. Section A, problem solving. Automation works designs and builds automated systems in the food and beverage industries that often require cooling of products and machinery. Localized cooling can be inefficient or unsuitable for some of these processes. I decided to make a model to show how centralized cooling works and to experiment with the control system. For my problem statement, to design and build a chilling system for centralized cooling of machinery and products, which runs on a local PLC, making it automatic and energy efficient. I added sensors so that the reason why I say energy efficient is because I added sensors, temperature sensors, so that when it detects a certain level of temperature, it would automatically switch off or switch on in this case. So if it reaches 40 Celsius, then it would switch on, and then it would go, the pumps would switch on, and when it reaches where the water has been cooled down or liquid, it would switch back off. My solution process. Since I am creating a solution for cooling demands, I researched chiller systems to help me understand how different types of chillers work and where they usually get used. I found that there are mainly two types used in water chiller systems. As you can see in this diagram by my slide, you can see a clear depiction of a air-cooled and a water-cooled chilling system that mainly gets used. So on your left side, you see the air-cooled chiller, a refrigerated unit that removes heat from a process fluid by using air to discharge the absorbed heat. And then on the right side, you will see the water-cooled chiller, a machine that removes heat from industrial process and equipment by circulating a cooling fluid. And as you can see in this diagram, you can see a clear view of a water cooled chiller. So you can see there, you can clearly see a cooling tower and a condenser and an evaporator. But in this case, for my small model, I am using a Peltier and not a cooling tower, which is expensive and big, and a condenser and evaporator, which is also really expensive and big. And then for where it gets applied, with a water cooling chiller would usually get used in the real world, would be in buildings, hospitals, factories, and data centers. So in hospitals, MRIs and CT scanners usually use a water cooled water cooled chiller, and for factories it would be wineries and milk, where a winery and where with wines it has to be a certain temperature, um, cool to a certain temperature, and with milk it also has to be cool to a certain temperature to work with. And then with data centers, it can't have water near the servers, so they can have heat, or they can't have water or heat by the servers, so they use a chiller to cool the servers down when it starts overheating. For section B, so the key components I used was a Siemens logo and a Siemens logo PLC, and pumps. I used two pumps, and I used a Peltier, and I used analog sensors. So the reason why there is a name AM2 is you'll see later that it will be shown uh, in my diagram and in my demonstration, and I used two temperature transistors, and I used tanks. I used three tanks, and for my innovation. So what makes it unique? So it is a small scale, um, and it uses a Peltier for cooling. So a Peltier, short description, um, it's a thermal electric cooler, a solid state semiconductor device that utilizes the Peltier effect to transfer heat when an electric current is applied, creating a hot side, replacing creating a hot side and a cold side. Section C. As you can see, this is my hand sketch. So you can clearly see the heatsink and the one pump at the bottom, and the cold tank and the hot tank, and the temperature sensors, which is currently says on this my hand sketch TT, and my load also has a TT, which is another temperature sensor, and then at the top you can clearly see a pump, one of my other pumps. And here you can clearly see my CAD sketch. So it's not that much in detail. This is only because I made um, all of my tanks and pumps separately in different files. So when I made the assembly, I put it all together so that I can have a rough idea of where I would place it on the stand itself. So this is my time lapse. This is my time lapse of um, where I drew everything on CAD, and alternatives that I considered. I, because I didn't have that much of an idea from the beginning of what a chilling system actually was and where it get used, and when I first got the explanation, I understood it as it's a fish tank that is it's almost like a fish tank, and it has to cool, and instead of heating the water, you're cooling the water. And so I was more thinking about instead using tanks and not 3D printing tanks. So yes, and this is my product testing. So in the beginning, while testing, it was a little bit messy. Water was splashing everywhere, but this was still me testing everything before I had the end product where it actually worked, and I was really happy. And this is another of way in the beginning of my product testing where I saw that because I didn't have a valve, it started spitting water out. So it did get the water in, but it was just more spitting it out. So everything was covered in water. So yeah. Section D. So the tools I used was a soldering iron to solder wires, a logo soft comfort to program the software, Fusion 360 to design everything, a handsaw to saw wood that was needed to build my stand, paint in can and paint cans, and so spray paint and roller to paint my stand, and ferrule crimpers to crimp the wires so that it can look neat, and copper wires not sticking out, and a box knife to cut the wires carefully, a hammer to hammer the nails in, pliers to pull out the nails that I not hammered in incorrectly, and then a caliper to measure everything properly and get the right measurements. And skills that I used was painting skills, and then programming on a PLC, and crimping to make wires neat, and the other hand tools I mentioned beforehand, and a 3D printer to print the 3D models, which is my tanks. And for this term, we had a project where we had to so for this term's project, which we have every term, this term's tutorial project was a where we had these festo kits, and the first festo kit that I programmed was the conveyor belt, and it was somewhat difficult in the beginning, and then it got easier. So we had to do all three, but this one was the first one that I had, so that I programmed. And this, as you can see, this is how it worked. I was really happy when it worked, and it wasn't as easy as you may think it was. And for my design sequence, so step one was research and then design on CAD. So a lot of research had to go into this, where I had to understand how a chillers work and what can I use as replacement to cool everything down, the water down, and then printing tanks. So the research came in handy because to make the 3D print so that it can be waterproof, it has to be a little bit thicker and done different. And step 3 was to start wiring and soldering everything, and then step 4 was cutting the pipes that I would be using that would um, draw the water from one tank to the other, and then building it, the stand, and painting it, and then finally assembling it and then testing it so that I can see if there was any flaws, anything that needed to be changed and reprinted. Section E. So for my research information quality, I use Gison. In the beginning you saw a clear picture, so they show a clear difference between the air chilling system and water cooling system, and they gave a good description about it. And then for the engineeringmindset.com, they provided the information and picture of how water chilling systems would look like and operate on a bigger scale. And then David from Automation Works that provided the information that was necessary and gave me introduction to chillers and how they work in facilities and different places. So with this, he could help me because they were my project is a smaller version of this big project that they were busy with, which was Bev 0, the bigger scale of my small scale chilling system. So he helped a lot with that, providing me with the information and what tools that where should I look for what I can use. And application of research. So through the research that I have done and found out that a Peltier would be a good choice, and for how I would be designing it and where would everything be placed. And it made me also think about the materials that I would be needing for this project. Section G. This is my activity log. So as you can see, a lot of my time was spent with theory because theory was not really my it was a little bit difficult to understand in the beginning, and then 22% of my time was spent with my project, and then there is my practical and my PPT, which we have with JC on a Monday and Friday, and then my tutorial project I put in 6.1% of my time. And then the most impactful PPD was the emotional and rational decision making. So rational decision making is the logical reasoning. So making a logical reasoning while emotionally deciding making is influenced by feeling and emotional brain with regulates our okay, never mind. So the rational decision making is where you as a person would make a decision and you would actually think about it instead of going head on in it, and you put time and effort in before making that decision and use facts for before doing anything. And then with the emotional It speaks for itself. You go purely on feelings, and why this stood out for me was because in different scenarios or situations, you would need to be rational or emotional, and majority of the time it's emotional when it comes to friends, family, and then in workplaces and such, or even with friends and family, you have to be rational sometimes because in each scenario there's reasoning behind why the person is making that decision. Technical difficulties. Okay, this one was fun. I used the wrong PLC. So because I didn't check the voltage and the first one that I used was a 24 volt PLC, and yeah, the Peltier itself can only take 12 volts. So I used the with the Peltier, and then only 3 days before this presentation, um, I realized, okay, my water's not cooling down, and yeah, I blew the Peltier by accident. So that was fun, not knowing that happened, but okay. And I had to redesign my 3D prints because I really good look a heavy lesson about always putting threads in, because if you don't put a thread in then you will get leakages. And then with programming, test everything separately and not all at once, because then you're gonna run into a lot of problems like I did. Technical successes. So my sensors worked after my sensors worked when I finally tested it. The third my third final test. So it finally worked. Switched on when the temperature struck a certain height, and then there was no leakages from my tanks because I put threads in, and then pumps got triggered by temperature sensors, which was a big that was actually a really big success for me. And the lessons I learned: double checking the wiring, because if you don't double check it, it's just gonna fall out, and that's not fun rewiring it. And putting threads in a 3D print, because it's not fun when that has to happen. And always checking the voltage, because you don't want to blow something up or blow yourself up or electrocute yourself. And ask for help when you're struggling. And test everything separately, because that saves a lot of time. And always wear gloves when painting, because clearly I did not learn my lesson from last term. So let's hope it doesn't happen next term. And make an assembly beforehand, and not later on. Saves you a lot of trouble with the measurements and changing a few things last minute. And then for future improvements, I would like to put indicating lights on so that it can be easier to read for others, and changing the tanks to something more tank-like and not 3D printing like. So this is my bill of materials. As you can see, the total sum is 7,229 rand and 14 cents. And for my time spent, so with 3D printing and building, altogether that would be 200 over 208 hours. And I would like to thank Nick. I would like to thank Nick and Kevin with helping me with everything and helping me to wire, and yeah. And I would like to thank David for giving me the idea of a chilling system, and David for Wednesdays when we work with him, and JC with the PPG on Mondays and Fridays, and Tani Elmer for pushing us to our limits and always giving us food. Now for the demonstration.